Welcome to the third and last part of week 5, in which we've been learning about decision analytic modeling. And in this last part, I am going to go through some principles of good modeling practice and then follow into an introduction to sensitivity analysis. And these good practice principles allow you to do good sensitivity analysis. So as we look at sensitivity analysis, we said that part of the attractiveness of decision modeling is its ability to handle uncertainty. And usually, at least one type of uncertainty has to do with the fact that usually you have a likelihood estimate, and this likelihood estimate in decision analysis is expressed in terms of a probability. But a probability is essentially an estimate of likelihood, but you don't know or not know if an event is going to occur. So I can say that there's a probability that in the next 12 months, I am going to win the lottery, and maybe my probability of winning the lottery in the next 12 months is 10%. I really wish it was 10%. So, but there might be uncertainty around that estimate. Maybe it ranges from 20% to 0.01, which is 1%. So sensitivity analysis allows you to estimate the impact on your results, on those results that we calculated in the last two parts. It allows you to estimate the impact on those results of varying this probability between these two ranges. So that's what sensitivity analysis does. There are some suggestions for good modeling practice, and these not just make decision models better, but they also make sensitivity analysis easier. So let's go through those before we talk about sensitivity analysis. The first one is balance, and decision analysis is about trade-offs between risks and benefits of choices, and one shouldn't have all the risks or all the benefits expressed in one of the choices. So if the model is unbalanced, it doesn't accurately represent the clinical policy problem, and therefore does not require decision analysis. So let's use an example. So we still have our Ebola example here. We have XMAP, cure, no cure, supportive treatment, cure, no cure. So obviously it captures the cure rate with or without XMAP, but it neglects the disadvantage of XMAP, and the disadvantage of XMAP is adverse events because it's a medication. So there is a downside to using XMAP. So a balanced model captures that, and the model that we use as an example had a branch for adverse events, and that provided balance in terms of the risks and benefits and the trade-offs therein, which are the rationale for doing decision analysis. So a good model needs to balance. It needs to have balance. The next recommendation is to only have 2 branches per chance node. Remember, the chance nodes are the circles, and logically and structurally there's no problem with having more than 2 branches. For example, in this not recommended example, you have serious injury and an individual might die, might get paraplegic, which means paralyzed for all 4 limbs, or might live without any paraplegia. However, what is recommended is that you model only 2 branches per chance node. So if you have the serious injury here, it goes into die, and then here it has survive. Actually, this shouldn't be paraplegia. This should be live. And if you live, you might live but become paraplegic, or you might live with no paraplegia. So this would be live but with no paraplegia. So this modeling setup is much better because it would allow easy sensitivity analysis. If you have more than 2 branches for a chance node, the sum of the chosen estimates during sensitivity analysis might exceed 1. If you run the model for any one run, the sum of the probabilities at a chance node might exceed 1, and that will complicate the sensitivity analysis. The next recommendation is not to embed a decision node. And embedding a decision node means having an initial decision node and a new decision node after the first decision node. The recommendation is to express all combinations of decisions as distinct therapeutic strategies. That means having a single decision node for each model. And this makes interpretation of the sensitivity analysis easier. And this is even more important if you have large models. So this is not recommended. Having two decision nodes is not recommended. So for this example, if you had fever and you had test for malaria, then treat, or don't test, and then you have another decision where you say, should you treat presumptively or not treat? The best thing to do would be to have three branches of the decision node right here, to have treat all, presumptive, test for malaria, or treat none. Now remember that having three branches at the decision node is fine. It's where it's a problem if you have it at a chance node. So at a decision node, no problem having multiple branches, but you have to remember the recommendation that you only model the options that are necessary to avoid complicating the model in general. The next recommendation is to do with branch linkage. And branch linkage means using formulas or formulae to link the different branches of the decision model. And the reason is unlinked branches make sensitivity analysis problematic and can lead to incorrect calculations. And here is an example of a model. You have this probability P die, and this is for treat all, TA. And you have another probability here, P die. And the reason we have these names for the probabilities is that when you have numbers like 0.2 or 0.3 in models, both in Excel or in other software like Triage, this becomes problematic to follow, and it's better to create essentially variable names. If you create variable names, modeling becomes easier. So if you have created variable names and you want to make modeling efficient, you can relate different variables by their variable names. So instead of having P die TA and P die, you can turn P die TA, this one, into a formula here. So P die TA is equal to P die times P die minus P die TA divided by P die. You make it a fraction and you relate those two branches, and this makes sensitivity analysis easier. The other recommendation is that the tree needs to have symmetry, and an asymmetrical tree doesn't have all the different options at chance nodes are the same for different branches. So here you have a patient with headache. They might have ibuprofen or acetaminophen. These are the choices. And ibuprofen causes GI bleeding. There's a probability of GI bleeding. But acetaminophen doesn't traditionally cause GI bleeding. So this would be unbalanced because you don't have the GI bleeding option. But to balance that out, you can have headache, ibuprofen, acetaminophen, and have GI bleeding for both, even if the probability for GI bleed for acetaminophen is actually 0 and no bleed is 1. So this provides symmetry, and symmetry is good because it simplifies sensitivity analysis. So modelers usually use clones, and these clones mean that for every subtree in the model, the outcomes or the options or the different branches are identical. Cloning means that they are identical. So this is another recommendation for modeling. Let's now talk about this idea that order does not matter. So, for example, should adverse disease consequences come before side effects of a drug as you build a model? And should disease probability come before testing for the disease? And the order doesn't matter because the analysis is the same either way. If you do the mathematics, the multiplication of branch probabilities and the rollback, it doesn't matter. But it's better to have a logical flow. So here's an example. You have your headache, you have ibuprofen and acetaminophen, then you have GI bleed, and the GI bleed might lead to missing work. GI bleed or not bleeding, bleeding or not bleeding, bleeding or not bleeding might lead to missing work or not missing work. Now, if you do it this way, headache, ibuprofen, miss work, and GI bleed, this order doesn't sound plausible. It doesn't sound as though it helps the explanation. However, mathematically, it would be fine. So it's recommended that you use an order that best communicates your model, because ultimately the reason for building the model is to communicate. So I would recommend this configuration, this modeling framework, and not this modeling framework because of the logical flow. But mathematically, the order doesn't matter. Let's move on to sensitivity analysis, and we've been speaking about it for quite a while now. So let's now discuss what exactly sensitivity analysis is, and it's the process of repeatedly analyzing the tree using different values for probabilities, outcomes, and cost. And the reason for doing this is to check for errors, and we people who are involved in modeling call that debugging the model. And then the other one is to assess uncertainty, like I said. And the types of sensitivity analysis are one-way sensitivity analysis, in which you vary one variable at a time. One variable is varied at any one time, and you see the impact of this on the results of the model at a time, one variable at a time. Multi-way is many variables, maybe two-way or three-way, so multiple variables are varied at the same time. And then you have what you call a threshold analysis, and then you can do best and worst case scenario analysis, and even other scenario analysis actually, if you have a scenario of interest. And then finally you can do probabilistic sensitivity analysis. Let's look at how to assess the tree for errors, and we call this debugging the model. And there are two kinds of bugs. There are structural bugs, and these arise when you fail to follow the recommendations we talked about in previous slides. And then there are technical or programming errors. And a good place to start is by changing one variable over its entire range, not just its plausible range. And if you do this, this is only possible actually if you have followed the rule of 2 branches per chance node. And you can run the model for the entire range of outcomes. And if you examine the graphs, you will find the bugs. And a bug indicates that either you found a significant new finding and you're going to write a nice paper, or it's a mistake. And sometimes you find symmetry issues and linkage issues if you have variables. And you can find other problems like typos and wrong variable names. So there's a range of potential mistakes that you can find. So here's an example of a one-way sensitivity analysis for our Ebola example. And on this axis we have survival, which was our main outcome of interest, at least for the decision analysis part, before we included costs. And one of the main variables in the model was the probability of adverse events for XMAP. So this is on this axis, and it ranges from 0.1 to 0.2. If you remember, the probability, the baseline probability was 0.5. And as we can see, with treatment with XMAP and supportive treatment across the entire range of adverse events, the plausible range from 0.1 to 0.2, treatment with XMAP still maximizes survival at the entire range of possibilities, of possible probabilities for adverse events of XMAP. So this is an example of how, if you do a sensitivity analysis, a one-way sensitivity analysis, it shows that the results are not sensitive to the probability of adverse events with XMAP, because varying them at the highest rate up to 0.2, which is the highest possible probability of adverse events that is plausible, you still see that treatment with XMAP here still maximizes survival. So this is an example of a one-way sensitivity analysis, and in this particular case it shows that the results in terms of survival are robust to the probability of adverse events, the range in probabilities of adverse events to XMAP. Now what about if we increase the axis on this scale and we vary the probability of adverse events for XMAP from 0 to 1, which means that everyone would get an adverse event. Now you will see that at some point treatment with XMAP becomes terrible. It becomes bad because too many people get adverse events, and if they get adverse events, they incur a higher probability of mortality. So at 0.5, at the probability of XMAP adverse events of 0.5, the choice between supportive treatment and treatment with XMAP is indifferent. And that's what we call the threshold probability. So at this point, if the probability of adverse events to XMAP is 0.5, then you don't know what the answer to the problem is because the survival is 0.65 in both cases. So we call that the threshold probability. And anything in terms of probability of adverse events with XMAP that is beyond 0.5 means that you would rather use supportive treatment instead of treating with XMAP because that would be what would maximize survival. So if the plausible range for XMAP was from maybe 0 to 0.6, it would mean that the results of the model are sensitive to the probability, to the range in probabilities of adverse events with XMAP. Here is what the results of a one-way sensitivity analysis would look like, and the variable of interest is probability of XMAP adverse events, and the outcome is mortality or survival. And remember that you run the one-way sensitivity analysis for all ranges and for all variables. That is the way to do things. And you have this column where you have the different variables. You have the base estimate, the baseline estimate or the base case estimate, and you have the range in another column. And then you have the threshold, and this is the parameter value within the range at which both comparators are equal, like we saw in the previous slide. Now in this case, in this variable of interest, 0.5 is outside of the range. And what that means is that this particular result is not sensitive to the range of plausible estimates for the risk of adverse events to XMAP. So the model or the results are robust to the range of risks of adverse events to XMAP. Now, if we had, let's say, the risk of death from an adverse event and the threshold was maybe 0.55, then here we would say yes. So sensitivity implies that the strategy other than the optimal one in the baseline analysis is preferred at some point in the range, i.e. the threshold value is within the range. If not sensitive, that means that the result is robust. So in this case, the result was robust to changing the probability of adverse events to XMAP. So this is how you would present results of a one-way sensitivity analysis. In multi-way sensitivity analysis, you vary 2 or 3 variables, and you usually start with those that are most sensitive as you do the one-way sensitivity analysis. So let's say in this example you have utility on this axis and prevalence on this axis, and the area in this box represents combinations of prevalence and utility, and this is where one or the other option is preferred. And the threshold line divides the two regions and consists of pairs of values at which the analytic results are exactly the same. So at these points here on the line, the results are indifferent. So that's the threshold line. So the baseline can be defined, and maybe the baseline here was X. And you know, if you have a three-way sensitivity analysis, you might add another dimension and make it a three-dimensional figure. In general, multi-way sensitivity analyses are not very common, and if you choose to expand your knowledge of economic evaluation, there are situations where you might want to do multi-way sensitivity analysis, but in general, they aren't very common. So that is the end of week 5, in which we discussed decision analytic modeling, and I hope that by now you know how to do a simple decision analysis and how to apply decision analysis to performing modeling for economic evaluation, to do economic evaluation. And I hope that we've learned a few rules that might help with building models, rules for building decision models, and that as we finished, you'll have had at least an introduction to the concept of sensitivity analysis. I would like to thank you for your attention, and I'll see you in the next week, in which we will discuss Markov modeling. Thank you very much.